Now, continuing on with 3.9, this is 3.9 related rates part 2. Remember the first part, I worked questions 1 through 4 from that handout. Remember that handout, there's a link for it, right? You can download it. It should be, the link for that to download should be right next to these video lecture files. Uh, it's also found on the Files tab within Canvas, but we're going to go right to number 5. 5 is saying the base of a 13-foot ladder that is leaning against a wall begins to slide away from the wall. Okay, so let's draw that out, right? Let's say there's the ladder. We have the building right here, right? And your ladder's basically falling down, right? It's starting to fall down. And it says when the base of the ladder is 12 feet from the wall and moving at a rate of 8 feet per second, how fast is the top of the ladder sliding down the wall? Well, what do we have right here? Remember the goal or the trick to working these was to figure out what kind of shape you're working with, right? Whether we had like a circle that was expanding, a balloon, a cone, expanding, decreasing, whatever, right? Or rectangle. Same concept right here. So what's the shape that we're dealing with? Well, looks like we have some kind of triangle, right? Got a triangle. So we could say, oh, this is X, Y, and Z, right? And then remember that once we figure out the formula, the next step was to figure out what we know and don't know what we're asked to find. We make like a checklist, right? So let's do that. We know. What do we know right here? Well, it says we have a 13-foot ladder, right? So what is that right here? X, Y, or Z? Well, the ladder's the thing leaning against the building, right? This is going to be the Z in this instance, okay? And it says when the base is 12 feet from the wall, well, that means it's this bottom portion right here, right? So what's this bottom leg called? That's X. So they're saying, oh, when X equals 12 feet, how fast is the top of the ladder sliding down the wall? What does that mean? How fast is the top of the ladder sliding down the wall? Well, how fast is it coming down the wall? Down the wall is the Y. But remember, when you see that phrase, how fast or rate of something, that tells you, oh, that's the derivative of something, right? So since it's asking about how fast is it sliding down the wall, that's the change in Y, or the derivative of Y with respect to time. So when X equals 12 feet, we're looking for dy dt, right? Dy dt is equal to the question mark. So this is all the numbers that they gave us, right? We got the 13, the 12. And from here, where do we go? What do we do with the other problems? Well, we derived the respective equation that we were working with. In this case right here, it was just x squared plus y squared equals z squared, right? And then from here, what do? We did d dt of everything, both sides. Now, because of that, right, that's implicit differentiation, because if you notice, we're taking the derivative of all three of these variables with respect to time, or t. None of these are t's right here, so we're always going to have a d something dt pop out. Meaning if I take the derivative of x squared with respect to t, we get 2x and then dx dt, right? Like the power rule. Same thing with the y. The derivative of y squared with respect to t is 2y dy dt. And the right hand side, well, that's going to be 2z and then dz dt. And now we need to fill in basically what we know, right? So we know that z is 13, that's not a problem. We know that x is 12, but we need a couple things, right? We need the y, and we also need what else do we need right here? We need a dz dt. And one more thing, right? What are we missing? Anything else that we're missing? No, we have everything. Something I forgot to mention from the we know column is we know dx dt, correct? Because it says the base, or when the base is 12 feet from the wall and moving at a rate of 8 feet per second. So that means x is sliding away, correct? It's moving at 8 feet per second. So we also know dx dt is 8 feet per second. So we need a couple things, right? We're still missing the y variable and the dz dt. Now, how are we going to figure those out? Well, let's look at dz dt really quick. Let's think about this. So remember, z is the ladder. The ladder is 13 feet. Now, if we're asking how fast is the rate of change with respect to the ladder, what could it be? Well, let's think about it for a second. Is the length of the ladder ever changing? Like, are pieces of it getting cut off, or are pieces being added to it at any point in time? No, the length of the ladder is always fixed. So if the length of the ladder is always fixed, it has no change in its length. If it has no change, then dz dt is equal to 0. Again, why? Because it's the ladder. The ladder is never increasing or decreasing as this in this problem. All right, so that's equal to 0. What about the y though? That we do need, right? And we can figure that out. How? Because we know x and z, right? Remember, coming back from Pythagorean theorem, if we know x and z, we can solve for y, right? Using Pythagorean theorem, this right here, we can say y is equal to the square root of z squared minus x squared. So y is equal to basically the square root of 13 squared minus 12 squared. And you're going to wind up with y equals 5, right? Because that's 13 squared is 169, minus 12 squared is 144, and that's the square root of 25, which is 5. Again, where did I get those two numbers from? It's because the length of the ladder is 13. The problem was asking specifically when x is equal to 12, right? When the ladder is 12 feet away from the building. That's where we're getting these two values from right here. And then the dy dt, we don't know that. That's what we are ultimately looking for. So we need to solve for that right there. So now we can plug all these knowns into our equation and solve for what's remaining. Okay, so 2 times x. Well, 2 times x, that's 2 times 12. dx dt was 8 feet per second. So I'm going to keep the units. This is 12 feet. This is 8 feet per second. And then plus 2y. Y we discovered was 5 feet. We're looking for dy dt, so that's the unknown. And all that's equal to 2 times z. Z we know is 13. And dz dt was 0. So now we solve for dy dt, right? Well, this is nice because the whole right-hand side's gone. Why? Because dz dt was 0. And now we basically have, what is that? 2 times 12 times 8, right? Or we could say, so we have 192 feet squared per second. Again, feet times feet is feet squared, plus 10 feet dy dt equals 0. And then from here, we just solve, right? Algebraically, we solve this equation. So I'm just going to move this 10 feet per second dy dt over to the other side. It doesn't matter which one you move, correct? It really doesn't matter. So I have 192 feet squared per second equals a negative 10 feet dy dt. And I just divide both sides by negative 10 feet. So we wind up with dy dt equaling negative 19.2 just feet per second. Notice the units cancel, or one of the feet cancels out, right? If I have a feet squared up top and a feet to the first and the bottom, you're left with a foot to the first, like that. And our answer is negative right here, right? That should make sense because remember, our ladder was sliding down. If it's sliding down, if the elevation is decreasing, it would make sense for the rate of it to be a negative value instead of a positive value, okay? So just take into account little things like that, like whether it's positive or negative. Again, if something's falling down, that is going to be negative. Or if you're pulling something towards you with respect to x, that would be negative because the distance of that is decreasing, correct, between the two objects. All right, now let's look at this question number 6. 6 is a baseball problem, baseball field. So it says a baseball diamond has sides that are 90 feet long. So we draw that out. We got something like this, right? All 90, 90, 90, 90. And it's saying a player 13 feet from third base is running at a speed of 20 feet per second. So they are basically right here, right? Here's our guy or whatever. And he's running towards third base. And they're saying that the person is 13 feet away, right? And they are running towards third base at a speed of 20 feet per second, okay? And what's the ultimate question? At what rate is a player's distance from home plate changing? All right, so what should we do first? Well, we kind of drew a picture, but let's make it a little clearer. I'm going to draw it like this. So now that we can see, oh yeah, we have a triangle, right? Like if we take this, right, you can see, oh, there's that triangle right there. Like now we could see, oh, this is 90. This is 13 right here, right? So as you can see, we're dealing with the right triangle again. We know we're going to have x squared plus y squared equals z squared. Now we just need to figure out what we know, what we're being asked for, correct? So let me go back to the sheet. All right, so it says a player 13 feet from third base is running at a speed of 20 feet per second. So this is, we could say this is y and this is x, and then we have z right here. Remember, z is the hypotenuse, it's always the longest side. Now, if the player is running towards, so we know x is 90, y is 13 or feet. If the player is running towards third base, right, at 20 feet per second, what does that mean? They're talking about this right here, this chunk. They're talking about this, right? He's running this way towards, this is third base right here. So they're running towards that, but with respect to letter, what letter are they talking about? The Y. So it's the Y that's changing right there. So think of it kind of like the ladder thing, right? Remember the ladder was falling down. This is falling down, or it's returning back to this point. If it's returning, then it has to be some kind of negative number. And in this case right here, it's going to be dy dt, because again, it's only affecting the y component. He's running towards third base, right? You can think of it kind of like that. They're running towards it at a speed of negative 20 feet per second. Really important, it was negative, correct? Because we're coming back, okay? If he was running away from third base, right? Or if he was running from first to second, for example, he'd be running away from first base, then that would be a positive value for the rate. But since he's coming back or returning to, getting closer like that, your value's negative right there. Now, do we know anything else? Or what else is the problem telling us? So we've used the 90 feet, we've used the 13 feet, and we've used the 20 feet per second as the change in y, or dy dt. The problem's asking us, at what rate is the player's distance from home plate changing? So what is that right there? What are they asking for? Well, remember, coming back to here, imagine you're running along, you know, this line towards the base. This amount here is always changing, right? Like when you first start, you hit the ball or whatever, and you start running, what happens? Your dashed line, what do you know? It would go out like this, right? Away from home. And then it would slowly arc, you know, up and then back down towards third base and then finally to home. So these blue dots, imagine from home base, they're always changing forever and ever and ever, right? Because you might have a triangle right here at some instant. Another instant, you could have a triangle right here. And that would always forever be changing, right? So the length of this blue line will always be changing, just like the length of this black line, right? That will always be changing forever and ever and ever as you go around the bases. And eventually, once you get back to home base, your distance would have been 0. So we want to know dz dt. Because again, they're asking us, at what rate is the player's distance from home plate changing? So from here out to wherever this black line is, right? Again, that's always going to be changing, because as I come or approach home base, this black dashed line will get smaller and smaller and smaller, right? Until boom, you get the home run. Now, let's go out there and derive our equation, right? Just like what we've been doing. You take the derivative of this, our triangle equation, with respect to time. And we did in the previous problem, right, with the ladder. It's the same thing, right? ddt of both sides. And you're going to get the same exact values again, right? Like we're going to get the 2x dx dt plus 2y dy dt and then 2z dz dt. Now, if we plug in what we have, though, we're going to be missing a few things, right? Like, what are we going to be missing right here? Well, we don't have a z component. We don't know how much that is, right? They didn't say that right there. We're missing that. So we need z. And we also need, what else? Because we want a dz dt. We have a dy dt. We also need a dx dt. We need those two things right there. Well, how can we find z? Well, remember with the ladder problem, we were missing, I believe it was y, right? How do we do that with the Pythagorean theorem? X squared plus y squared equals z squared. Well, if we need z, right, we can say z is equal to the square root of just x squared plus y squared, because we have x and y. We have z equals square root of 13 or 90 squared. 90 squared plus 13 squared. So when you work it out, we get z equals 90.93. Now, I know I said before, oh, leave your answers in exact form with the pies and all that stuff. Why is he putting a decimal right here? in the directions for this on the web assign, it will say, oh, round it off to a certain place, whether it's 2 decimals, or it could say the hundredths, right? This 2 decimals and hundredths are synonymous. It means the same thing. So just pay attention to stuff like that. So we have the z. What about the dx dt, though? So dx dt is how fast the rate or the length of this is changing right here. Well, it's not. It's always constant. It's kind of like the ladder, right? Remember the ladder? It wasn't sitting there and it wasn't getting shorter or longer, right? Only the length of z is getting shorter or longer in this case. The change in the length of this distance of 90 feet, right, is never going to change right here, because as a standard, just like the ladder is always 13 feet, right? The ladder is always 13 feet in the last problem. The distance from home plate, according to this line here to third base, will always be 90 feet. That distance will not change, okay? So dx dt is equal to 0. So now we have everything, right? We can plug it all in and we can solve for dz dt. All right, so we start right here. We have 2 times x. X was 90 feet. Dx dt was 0 plus 2. Y was 13 feet. And then times dy dt, that's negative 20 feet per second. And that's equal to 2 times dz dt. Or 2 times, I'm sorry, z, which is 90.3 or 90.93 feet, times dz dt. So I'm going to clean all this up. So this disappears right here, right? Because 0 times all that's just 0. So you're left with 2 times 13 feet times negative 20 feet per second equals 2 times 90.93 feet per second, and then times dz dt. And then from here to solve, right, what do we need to do? Just divide both sides by this component right here. All right, so calculator, right? And you wind up with dz dt equaling negative 2.859. So if we round it to 2 decimal places, it's just negative 2.9, right? Because this 9, I'm sorry, 2.86. 2.86 feet per second. So for Z, that was 90.93 feet, not feet per second. So make sure y'all adjust for that, okay? Erase that right there. Z was just 90.93 feet. And that way we're going to be left with feet per second. Why? Because one of these feet cancels out, and then you're left with the feet per second. Okay, now let's look at 7. It's saying a boat is being pulled towards a dock by a boy. All right, so here's the dock. You got the boy. And the water. The rope is being pulled in at 3 feet per second. The distance from the boy's hands to the dock is 4 feet. How fast is the distance between the dock and the boat decreasing when it is 30 feet from the dock? So, what do we do right there? Well, we have another triangle, right? Got a triangle right here. And let's just fill in what they're giving us. So they're saying the rope is being pulled in at 3 feet per second. So this is the rope right here, right? Z is the length of the rope. But if it's being pulled in at 3 feet per second, what does that correspond to? That's dz dt. So we know dz dt is equal to, and if the rope's being pulled in, that means its length is decreasing. It's going to be negative. So that's negative 3 feet per second. And it also says the distance from the boy's hand to the dock. So from here basically to here, imagine that. That's 4 feet. So we know y is equal to 4 feet. Then they're asking us, how fast is the distance between the dock and the boat decreasing when it is 30 feet from the dock? So they're saying, oh, x is 30 feet. But we want to know how fast is this distance here, right? Because the boat's over here and it's getting pulled in towards the dock. How fast is that distance decreasing? So dx dt is the question mark right here. So again, we're just starting with Pythagorean theorem. X squared plus y squared equals z squared. And then of course, when you take the derivative with respect to time, just like we've done with the previous two, you're going to get the same generic equation. We're going to wind up with, the 2x dx dt plus the 2y dy dt equals the 2z and then dz dt, just like that. All right, so we're missing a couple things, right? Like, what is dy dt? What does dy dt equal in this case right here? Well, let's think about it, right? It's kind of like that ladder issue where this distance right here is never changing. The boy is he's like a robot. He's perfectly pulling in the rope and he's not moving up or down at all. He's just keeping himself level and he's just pulling in. So only x and z are actually changing. The height of this is never changing. It's kind of like the ladder. The length of the ladder never changed 2 problems ago. It was always 13 feet back then. So if there's no change in that, that means dy dt has to be 0. But we're missing something, right? We need the z. How can we find z? You can find z with Pythagorean theorem, right? So for z, again, just like what we did the last problem, z is equal to the square root of x squared plus y squared. It's Pythagorean theorem. So in this case, we have 30 squared plus 4 squared. So you get z equals 30.27. Okay, so we have that. And now let's plug in all these values and solve for dx dt. So we have 2, x is 30 or 30 feet. dx dt is the question mark, right? Because that's what we're looking for. Plus 2 times y is 4 feet. dy dt was 0, and that's equal to 2 times 30.27. And then dz dt we saw was negative 3 feet per second. So I'm going to put my units in right here. That's feet, 30.27 feet. This goes away, right? Because that's 0 times all that stuff. So now we have basically, 60 feet dx dt equals, I don't know what all this is. Negative 181.62 feet squared per second. Again, feet squared because feet times feet is feet squared. And then we divide both sides by 60 feet. And then you wind up with negative 3.027. And again, if they say rounded to 2 decimal places, we would say negative 3.03. So just, and that would be feet per second. Why? Because if you have, again, feet squared up top, feet on the bottom, one of them gets knocked out. As far as the decimals, watch the directions, okay? Usually they will specify round to 2 decimals or 3 decimals or whatever. Normally the problems that have pies involved in them, like volumes of cones or spheres and stuff like that, they won't tell you to round. They're going to want you to leave it in something with the pi. And remember to type out pi on WebAssign, literally type on your keyboard pi, right? And then it'll spit out the pi symbol. But for the others, if they call for a decimal, then do it. If not, you just leave it in exact form. So remember, the steps for solving these is, the first one is figure out what formula, geometric formula you're working with, right? Like you could have squares, circles, spheres, cones, triangles, rectangles, whatever. Then you just make a list of what you know and don't know, right? Anytime they give you, whether it's like a length, a width, a height, a radius, and then when you see that phrase, change in, rate of change, decreasing of, increasing of, that signifies that's the derivative of a specific letter, right? Because that's all that it is. Derivative is a rate of change. Now remember, if it's something going away from you, then that, or it's expanding, that distance, or I'm sorry, that rate of change would be a positive number. But if it's decreasing, right, or it's coming towards you, or like with the baseball, you were running back towards the base, or in this case, we were pulling the rope towards us, that rate of change would be negative, right? So you plug in all those values, and sometimes we'll be missing something, right? Like with these particular triangle problems, out of the, we had 6 variables, right? 1, 2, 3, 4, 5, 6. And we initially had 4 out of the 6. But remember, in order to solve an equation, you can only have one unknown. So we had to solve for that 5th unknown, right? And we did that with the Pythagorean theorem and trying to figure out the length of the missing side. So sometimes you'll have to do that as well. Well, you'll know by when you make a checklist of what you know and don't know. So just keep, it's a system, right? It's just being organized. I know these problems are very long, but if you keep things organized and write everything out, then once you get to this step here, when you have everything, listed out, you're like, oh yeah, just plug stuff in. And afterwards, you get a basic algebra equation. You should always get some kind of basic algebra equation like this in the end if you've substituted or you have the correct numbers. Again, if you get to this step where you're substituting values in, and all of a sudden you have a dx dt and a y, or a combination of, more than one unknown, you need to go back, okay? Because you should be able to, again, figure out all the variables except for the unknown that the problem is asking you about. All right. So this concludes 3.9.